volume in Cartesian coordinates, that for conservation of mass, we must have and if rho is constant, then this reduces to this is what we call incompressible flow. And end of the class, we mentioned that in many engineering situations, you have a geometry for which cylindrical coordinates would be more appropriate. So then we need to see what does the condition for conservation of mass look like in cylindrical coordinates. So let's have a look. Okay, so if this is x-axis and this is z-axis, then typically the cylindrical coordinates, we replace the x and y coordinates by r and theta. So we take polar coordinates in x and y. So that would look something like this. So if this is your x-axis, the theta measures the angle from the x-axis and r measures the distance. So this measures r, and in addition to that, we have the distance z. So then in order to write the conservation of mass in cylindrical coordinates, we'll once again take an element in cylindrical coordinates. So an element which spans the volume from r to r plus dr, theta to theta plus d theta, and z to z plus dz. So what would that look like? So if you go from r to r plus dr, it would be something like this. If you go from theta to theta plus d theta, that would mean moving away from this. This would be d theta. This would be dr. And from z to dz would be dz. So then let's draw this. So r to dr, this is the way it goes. If I change theta, it goes through an angle d theta. And if I change dz, this is what it would be. So this side of the element is dr. This side, if I see, this arc would have a length r into d theta. And this is where the difference comes, that this is, arc and this arc are not of the same length. So this is r into d theta. So if I change my angle through theta, if I'm at a distance r from the axis, then I go through a distance r d theta. But if I'm at r plus dr, then I would go through a distance r plus dr into d theta. So this would be r d theta, while this would be r plus dr into d theta. dz remains unaffected, so these elements are all dz. Now conservation of mass says and dm system by dt by Reynolds transport theorem is so once again I need to evaluate these terms. So for a small element, and the element here has volume, so then since this is an orthogonal coordinate system, the dr and the r d theta are at right angles, and both are at right angles to dz. So the length into breadth into height will give me the volume. So if I see the volume would be, okay, the volume enclosed between theta and theta plus d theta, that would be yes. Yeah. So for the entire 2 pi, the area is pi r square. So then for an element enclosed by theta and theta plus d theta, so if this is theta and this is d theta, then the area enclosed in between is half r square d theta. So therefore, if I take an element dr of this, it would be half r plus dr whole square minus r square d theta is equal to half r square plus twice r dr plus dr square. This cancels with this. So to leading order, if I assume that dr is small, then in the limit dr going to small, this would be small, this would be negligible compared to this. So I can approximate this as r, sorry, r dr d theta, which I can write as dr into r d theta. So it's as if it's a rectangular element with one side dr and the other side as r d theta. And the variation in r is of higher order and therefore can be neglected in the limit dr tending to 0. So this area is r dr d theta, and therefore the volume of this element would be this base area into the height. So that would be, so the volume here would be r dr d theta into dz. Okay, so once again, I've assumed that r, theta, z, and t are the independent variables in the Eulerian description, and therefore r, theta, z do not change with time. So then this derivative becomes this. So then we need to evaluate so then I have an element so the r coordinate changes in this direction. So these are the these two faces are the faces which are in the r direction. So rho v dot dA, v if I express in cylindrical coordinates, it will have components. So v in cylindrical coordinates I think here I have to use ER, E theta, EZ. So those are the unit vectors along in the R, theta and Z directions. And this is an orthogonal coordinate system, which means ER, E theta and EZ are mutually at right angles to each other. So then the R faces are have their normal in the R direction. So when I evaluate V dot dA for the R faces, only the R component of V contributes. So that into the area would be, so the magnitude of VR into the magnitude of area, that would be V dot dA. So dA is in the R direction, ER dot ER by definition of a unit vector, that becomes unity. So it will be VR into whatever the magnitude of area. So then the unit normal at R plus dr is in the positive R direction, and in the at R is in the outward normal to the volume is in the negative direction. So I'll get a positive contribution from to the mass outflow. So this is the rate at which mass flows out. So that has a positive contribution from this space and a negative contribution from this space. So contribution from the R faces. So contribution from the R faces would be equal to the so rho at R plus dr into VR at R plus dr into the area. The area of this face is R plus dr d theta into dz. And at R, the VR, the area element has magnitude R, sorry, sorry. So it is R plus dr d theta into dz. And on this space, the area has magnitude R d theta dz, and its outward normal is in the minus R direction. Therefore, when I take the dot product, it will give me a minus sign. So if you see, this term involves both rho, involves all three, rho, VR and R evaluated at R plus dr, and this involves the same three quantities evaluated at R. So this I can write as so if I expand this in Taylor series and keep only the leading order term, then that would give me you'll notice that here we haven't got dv because dv has a dr into an r d theta into dz, so that r is missing over here. So if I look at the theta faces, so theta changes in this direction. So therefore, these are the theta faces. So the area of the theta faces is dr into dz. So this one as well as this one have the same area. And the normal to the theta faces is in the theta direction. So this is the theta direction. This one has a normal in the negative theta direction. The positive theta direction is the direction in which theta increases. So this is the direction in which theta increases. So this which is at surface which is at theta has a normal in the negative theta direction, and this which is at theta plus d theta has a normal which is in the positive theta direction. So therefore, the contribution from the theta faces would be rho at, so rho a dot rho v dot dA is what I need to evaluate. So it would be into the area which is dr into dz. So if I Taylor expand this, then to leading order I'll get once again that factor r has not come in here. So now I have to consider the z faces. So the z faces have that base area. That base area which we saw is like r dr d theta. So once again, the face at z has a normal in the negative direction, and at z plus dz has a normal in the positive direction. So accordingly, the contribution from the z faces would be equal to rho at z plus dz vz. The normal is the normal to the z faces in the z direction, so only the z component of v makes a contribution. This evaluated at z plus dz into the area which is r dr d theta minus this time all the factors of dv have appeared. So now, so then So it was del by del R of rho V. So this I can write as R rho VR. And here I had only dr d theta dz. Again, if I can consider the contribution from the theta phases, del by del theta of rho v theta, and I have dr d theta dz. So the conservation of mass said let me divide by the volume of the element, which is r dr d theta dz. So these two terms which did not have the factor r, there a factor of 1 by r will come in. So d theta. So this represents the conservation of mass. Now, this must be the same equation in vector form, regardless of whatever coordinate system we are using. So this again must be which means so rho Vr, rho V theta, and rho Vz are the r theta and z components of the vector rho V, which means if I have any arbitrary vector A, So then this equation, if I expand out, I can write so del rho by del t plus 1 by r. So okay, my equation is del rho by del t plus 1 by r del by dr r rho dr. So I can write this as now if you see del dot A is 1 by del r of RAR plus 1 by r del A theta by del theta plus del AZ by del Z. So it is exactly a similar expression with A replaced by V. So then this must be your, this term is this, obviously. This term must be, and therefore this must represent V dot grad rho. So a vector equation is an equation which expresses the relation between vectors, and so In compact vector notation, the equation must remain unchanged regardless of what coordinate system I use. So in vector form, del dot rho v was v dot grad rho into rho divergence of v. So that so this expression must remain the same. So then, now that I have the explicit expression in terms of components, these terms represent rho del dot v. This must represent v dot grad rho. So v is equal to now this dot grad rho must give me this, which means grad rho must be equal to then this dot this will give me Vr del rho by del r. That is what I have. The E theta must be 1 by r del rho by del theta. Then the V theta comes from here and the 1 by r del rho by del theta comes here. So this is the expression for grad of rho. For an incompressible flow, rho equal to constant, all these terms disappear. Assuming rho is non-zero, it is this which must be zero. So you one thing you'll observe that the derivative with respect to theta always comes with this factor of 1 by r. So here in the grad you have 1 by r del by del theta. Here in the r component you had del by del r. In the z component you had del by del z. Whereas in the theta component you had 1 by r del by del theta. This is expected because the gradient is derivative with respect to a distance. So a length variable must be there in the denominator. Now r is has dimensions of length. Z also has dimensions of length, but theta is an angle and is dimensionless. So it doesn't have the dimension of length. So an r provides the dimension of length. So we can make out that with the theta, this r must be there in order to satisfy the right dimension. Otherwise, looking at it another way, if I change r from r to r plus dr, I move by a distance dr. If I change z by dz, I move by a distance dz. If I change theta by d theta, then the distance through which I move is not d theta but r d theta. This factor of r is required for dimensional considerations also, and we know that if I change theta, if I'm at a distance r from the axis of symmetry, then the distance through which I move is not d theta but r d theta. So therefore, when I take gradient, how much does rho change So if I'm taking a gradient of rho, how much does rho change as I change theta? So what is the change in rho divided by the distance which I move through, and that distance is r d theta and not simply d theta. So therefore this r comes together with the del theta. Now this seems to be a little more puzzling. I don't require an 1 by r for dimensional considerations. So in order to be dimensionally consistent, if I have a 1 by r here, I must have an r over here to compensate for that. And then this is the expression I have. So why is it not simply del Vr by del r? Instead it is 1 by r del by del r Vr. So let's look at a one-dimensional situation. Pure radial flow. So I'm assuming that V theta and Vz are 0 and Vr is a function of r only. In that case, if I consider a radius r1, the flow, the outflow through this cylindrical area would be two pi r1 into whatever the length in the z direction. So this is the area through which the flow is occurring into Vr at R1. Similarly at so if I have a steady flow and there's no accumulation of mass, then if I draw another circle of radius R2, whatever flowing out from here must flow out from here. So therefore, this must be equal to this. Now twice pi h do not change with r. So then I must have R1 into VR R1 is equal to R2 into VR R2. So therefore, RVR is equal to constant. So that is why in the continuity, what matters is the rate at which RVR changes, because the outflow is proportional to the area at that radius, and the area increases linearly with radius. So this equation you can also so in the condition of incompressibility I can write as So this is how we write the condition for conservation of mass in cylindrical coordinates. So I'll leave it as an exercise to you. Okay. Next, we have to go over to the momentum equation. So it's around 11:47. So let's take a 5-minute break, and after that we'll resume with momentum equation. So during the break, in case you have any question, you can ask. Okay, coming back. Now let's consider I think once again we'll start from the Reynolds transport theorem. Now in this case, our property B is a vector quantity. So it's effectively, so in three-dimensional space, it's effectively three equations for the three components. So B is equal to it's often denoted by capital P, which is mass into velocity. That means beta is equal to V. So the linear momentum per unit mass is the velocity. So then I have so in this equation beta is V, so this becomes and the rate of change of linear momentum would be the external force acting on the system. So there are two parts to our equation for conservation, equation for momentum. I don't say conservation of momentum because momentum is conserved only if the force is zero. So in general, so what I'm writing is the momentum equation, which means it will express the law that the rate of change of linear momentum for a small element. So if it's a small element, I can consider that as a point mass. So then the rate of change of linear momentum of that will be equal to the force. So I have to, in order to write that equation for a fluid, I need to address two parts of the problem. One is, what is the rate of change of linear momentum of the fluid? So for that, I have to evaluate. So for that, I have to evaluate these terms. So for that, I need to evaluate these terms. To get what is the rate of change of linear momentum of the system, and then I have to write down what is the force acting on an element. So what are the various components which can contribute to the force? So if I have a fluid in a certain region which is flowing, in that case, I could have some forces which are acting throughout the volume of the fluid. These are called body forces. So a common example of that would be the force of gravity. And I could have um, forces which are acting on the surface. So a common example of that would be pressure. So if I consider an element, the so my I'm trying to concentrate on, so I'm concentrating on the rate of change of linear momentum of the fluid contained in a certain volume element. So then I must consider all the forces acting on it. So there could be pressure exerted by the surrounding fluid on the fluid inside that element. So I can have pressure forces, and apart from that, I could have uh, viscous forces. So viscous forces you may or may not have encountered. Have you encountered viscous forces in your discussion in school?
Yes, like only the formula F equals to minus eta A dV by dx.
Okay, so the one-dimensional case that you know. So for a more general geometry, what is the expression for viscous stresses that needs to be introduced. So ideally one would have wanted to do a derivation, but since this is a first course, we'll not be able to derive it, but we'll have to just tell you how it is derived and what is the final result. So you're familiar that there exists something called viscosity. So if you have velocity shear, then because of velocity shear, if I consider any imaginary plane inside the fluid, then the fluid on either side exerts a tangential stress, which is the viscous stress. But then the tangential stress is not the only stress which viscosity can produce. Viscosity can also produce normal stresses. So what is the general expression for viscous stresses? That we'll have to state, and from that determine what is the force on an element. Okay, can you see this pointer? A pointer near F, can you see it?
Yes, sir.
Okay. So then the pointer due to the pen seems to work. The mouse doesn't seem to be getting into problems. Okay, so let's tackle this problem part by part. So the rate of change of momentum of a system must be equal to the total force acting on the system. So let's first try what is the rate of change of momentum of a fluid element. So the rate of change of so Newton's law applies if I consider a certain mass, a certain fixed mass of fluid. So if I'm following a certain mass of fluid, then its rate of change of momentum must be equal to the force acting on the element of mass. Now, in order to apply that in that form, I would have to follow a certain element of mass of the fluid, which is not convenient when I have fluid flowing through a system, because as it flows through, as the fluid flows along with time, it moves from one location to another. And if I have a steady flow situation, in that case, if I follow a material element, its velocity may not remain constant. But if I have a steady flow situation, then the velocity at a certain position would remain constant. So once again, if I have a tank of water, from an inlet pipe, water is flowing into it and it's leaving through an exit. In that case, once it reaches steady state, velocity at this point and velocity at this point are not the same. But so if I follow the fluid, I would have to keep track of the change of velocity as it traverses its path. So both the magnitude direction change as of the velocity change as the fluid flows along. But if I sit at a certain position, in that case, the velocity remains unchanged. So therefore, it would be preferable to have an expression for rate of change of a system. Now, this law that the rate of change of linear momentum is equal to the force applies to a certain mass of fluid. So this this equation applies to a certain mass of fluid. Now, if I try to track that mass of fluid, then I would have to handle the problem of velocity changing with time, even for a steady fluid. So what I do instead, that at any instant of time, I can relate what is the change or rate of change of momentum of the system to the rate of change in the control volume through the Reynolds transport theorem. So then, so I know that rate of change of momentum is equal to force applies to uh, to the system and not to the control volume. But the rate of change for the system can be related to the rate of change for the control volume. So therefore, in this equation, if I write the rate of change for a system in terms of the control volume, then I can apply this relation to write an equation in terms of control volume. So I know that dp system by dt is equal to f on a system. Now at a certain instant, dp system by dt is related to the properties in the control volume through this equation. So the dp by dp system by dt I can write in terms of control volume variables. And at a certain instant, if the system boundary matches with the control volume, the f on the system and the f on the control volume are the same. So to evaluate dp system by dt, I use the Reynolds transport theorem and write the expression in terms of values in the control volume. So let's write that explicitly. So let's write that explicitly first. So now let's take once again, let's consider then let me consider this equation component by component. So in vector form it was f the x component of f would be fx. Now this integral is a vector quantity. So the x component of that would be this. The x component of this, now here I have a v dot dA. So v dot dA is a scalar quantity. So the x component of this would be, this is a vector, so it will be the x component of this into now let me consider an element of volume like this.
Sir?
Yes.
Sir, in fx, sir, the v dot dA is in direction x direction, right?
No, v dot dA is the scalar product, so that is a scalar.
Okay, sir. Yes.
So therefore that has no direction. So the direction comes from the direction comes from this. So that is why I take Vx of this.
Yes, sir.
So then for the volume element, so okay, the first term I've been able to, the first term here I've been able to evaluate. Then I have to consider the I have to consider the surface integral. So then this surface integral must be over the entire bounding surface of the elemental volume. So then it has contribution from 6 faces. So if I consider the x faces, so x faces are these two faces. The at x plus dx, its outward normal is in the x direction, and at x it is in the negative x direction. So therefore, the v dot dA for in the, so if I consider, okay, so let me consider the two x faces. So let us say this is at x and this is at x plus dx, because that is what the coordinate system looked like. This is x, so if this is x, this is x plus dx. So the contribution from the x plus dx would be Vx at x plus dx into rho at x plus dx into v dot dA. So at x plus dx, the outward normal is in the positive x direction, so it's only the x component of v which will contribute to this v dot dA, and its value is at x plus dx into the area which is dy into dz. That does not depend on the value of x, minus Vx at x into rho at x into Vx at x, and the minus came because the v dot dA is negative, because the unit dA is in the negative direction and the Vx is in the positive direction. But so that gave us the negative sign, and then the magnitude of the area is dy into dz. So all this contributes. So then this is like so these are the two y faces. This is at y and this is at y plus dy. So then the contribution from these at y plus dy, I'll get Vx so what I'm evaluating is the contribution to this integral from the y faces. So the first term in the factor in the integrand is Vx, then a rho again evaluated at y plus dy into v dot dA. So the dA is now at y plus dy. The dA element has unit normal in the positive y direction. So the part of v which will contribute to the scalar product will be Vy with a positive sign into the area, which this area is dx into, sorry, this is z, dx into dz. Then the contribution from the y face, then the contribution from the face at y, not at y plus dy, will come with a negative sign because the dA is in the negative y direction, and v, the component of v in the y direction is positive, is plus Vy. So when I take the scalar product, it will give me a negative minus
Sir?
Yes.
Sir, your screen is freezed.
Is it? Let me see. Okay, can you see now?
No, sir. Sir, like it's showing the that contribution from two Y phases.
No, sir, it is correct, clear.
No, let
Sir,
me
so
write, because actually I deleted, but I have got back my mouse cursor. So let me just write down. Okay. So it was dp system by dt is equal to if okay, now can you read?
Yes, sir.
Okay. So there was some problem. I just closed my whiteboard and restarted it. So now I think things are back again. So then we had shown that, okay, the x component of this was so this is what we were writing. So then we showed that del by del t for the small element which we were considering. So then we had started discussing the contribution from the control surface. So this is as far as we had done. Now we said let's consider the contribution from the y phases. So let's say I have one phase at y and the other phase at y plus dy. Then so what you have to consider is a contribution to this integral from the y phases. So the Vx and rho it will make contribution from the face at y plus dy and the face at y. Let's first consider the face at y plus dy. It has a unit normal in the positive y direction. So first is the Vx rho, which has to be evaluated at y plus dy. And then comes the v dot dA. So the dA is dz into dx ey into that dotted with v. So since so for this the dA is equal to dz dx into unit vector in the y direction, which is j. So this dotted with v, so v dot dA would be so this v has vxi plus byj plus bzk. So when I dot with this, it's only the vy which will contribute. So it will give me vy into dz into dx. So this has to be evaluated at y plus dy. So it will be vy at y plus dy into dz into dx. When I consider the contribution from the face at y, Vx rho will have to be evaluated at y. And v dot dA, now dA over here on this side, dA is equal to minus dz dx into j. So the outward normal is in the negative j direction. So it is vz vx into minus j. So when I take the dot product with v, so v dot dA will be equal to minus vy dz dx. So I have to put the minus here. Sorry. So it was minus vy dz dx. So the vy would have to be evaluated at y into dz dx. So again, Taylor expanding this. Okay, so let me write it in a little more compact form. So if I Taylor expand this, so if I compare the contribution from the x faces and the contribution from the y faces, here I had this factor dx, dy, dz. Here it has come in a different order, but ultimately it's the same expression dy, dz, dx. So it's again the volume of the element. If I consider this term, here I have a del by del x, here I have a del by del y, then the Vx rho are same. And since I'm taking, since this V came from the x, from the consideration which component of the equation I am considering. So I was considering the x component of this equation. So in the x component of this equation, this first V will always be Vx, and this is a scalar quantity. So this remains the same whether I'm considering contribution from x faces, y faces, or z faces. So in both cases, it is Vx rho here, Vx rho here. Now comes the difference, the V dot dA. The dA for the x face is in the x direction, so that brings in Vx. The dA for the y faces is in the y direction, so that brings in y. Similarly, if I consider for the z faces, that will bring in z. And when I consider the two faces, if it is the two faces at different values of x, then the net contribution would be proportional to the derivative with respect to x. When I consider two y faces at two different values of y, then the net contribution would be proportional to the derivative with respect to y. Similarly, if I consider z faces, it will be proportional to derivative with respect to z. So by analogy, I can write now, just as in the Reynolds transport theorem, we had an extensive property called capital B. We also defined the corresponding intensive property, which is beta, which is B per unit mass. So similarly, since I'm dealing with an elemental volume, now when I'm considering a system, then it's relevant to consider per unit mass of the system remains constant. When I'm considering a control volume, it is more convenient to talk in terms of per unit volume. So if I see the force on this elemental volume is given is equal is related to the rate of change of momentum in the control volume by this. So the terms which represent the rate of change of momentum, that if you see is proportional to the volume of the element. So instead of talking about force on the element, it would probably be more useful to talk in terms of force per unit volume. So then I define a small fx, which is capital Fx by that would be equal to so this is what it would be. Now, just looking at this expression, it seems similar to what we had for the continuity equation. Now, continuity equation told us that so here we could make out what it was. These three terms, which I have written out explicitly, are simply the divergence of vector rho v. Now, this term appears a little more puzzling, because whatever I have in these brackets has a Vx and a has two vector components of vectors. So I have a Vx and a Vx here, and here I have a Vx and a Vy. So this seems to involve two directions. So can we in some way simplify this? So then let's try to expand out this expression and see if we can simplify it. Now let me take some of these terms. So the terms which have the factor Vx, this I take, then I take this term, next I take this term, next I take this term. Now for conservation of mass, I know that the entire expression which is there in the first square bracket, this has to be 0, regardless of whether it is compressible or incompressible. We know that if mass has to be conserved, this has to be 0. So therefore, I started with this equation which we had derived, which was the x component of the momentum equation. So from that we found that this is the equation which the velocity has to satisfy. So so far I have left the evaluation of the force unaddressed. So assuming that I know what the force per unit volume is, if I know that force, that must be equal to this. And this expression appeared a little baffling because it within the bracket it had quantities which had two vector components, so we didn't know how to interpret that. So we decided to expand out this right hand side, and using the condition of incompressibility, we are able to show it reduces to this. So then this must be equal to fx. So the right hand side fx is equal to something. That something we have shown is equal to this. So quite a few terms in that expanded expression cancelled because of the conservation of mass. So finally we were left with this. So this must be equal to fx. So similarly we have from the y component you can show Now this expression, let's try to see how we can write this in vector form. If I consider the terms on the right hand side, these are the x, y, and z components of the vector f, where f is the vector force per unit volume. Its components will be fx, fy, and fz. So if I know the components of force in each direction per unit volume, that constitutes a vector which I can write as vector f, the force per unit volume. Similarly, these three expressions are the x, y, and z components of del v by del t. So if I have v is equal to vxi plus vyj, then if I take the derivative with respect to v, the unit vectors do not change with time. So therefore it is only the components which can change with time. So then these are the components which I have here. So this would be like rho del v by del t. Now let's come to this part. So everywhere I seem to, it seems there is a certain operator acting on the components of v. So I have an operator Vx del by del x plus Vy del by del y plus Vz del by del z. This is an operator acting on Vx, Vy, Vz. So that gives me the expression which I have in the x, y, and z components. So then let me consider the operator v dot grad. So this is Vxi plus Vyj plus Vzk dot I. The gradient operator is this. So then the dot product would be a scalar operator. Now the scalar operator involves differentiation with respect to x, y, and z and multiplication by vx, vy, and vz. Now the differentiation, that is where care needs to be taken. The unit vectors I, j, and k do not vary with x, y, and z. So regardless of where I am, the unit vector always points in the same direction and therefore has the same value. So therefore, when this operator acts on this, it acts the derivatives only give me non-zero contribution when I differentiate Vx, Vy or Vz. Derivatives with respect to derivatives of I, J and K with respect to X, Y and Z are identically zero. So it is as if this differentiation acts only on the components and not on the unit vectors. Now this is applicable for Cartesian coordinates where the unit vector points in the same direction regardless of what value of X, Y and Z I am at. So if I consider this, the unit vector, so if my coordinate system is X, Y and Z, the unit vector I, it points in the same direction regardless of where I am. Now you have to keep in mind that this is not true if I consider polar coordinates. So if I consider polar coordinates, and I measure theta from here and r in this direction, in that case, my ER is in this direction and E theta is in this direction. Now if I go to this location, my ER would have changed direction and my E theta would also have changed direction. So for a cylindrical coordinate system, the situation would be more complicated, but here I can assume that these differentiations act only on Vx, Vy and Vz and not on Ijk. In that case, so let me rub out all this. So then this would be so this acting on this gives me Vx del Vx by del x in the I direction. Again, this acting on this gives me this. So in this way, and so the x component of this is this, which is exactly what I have in the x component of the momentum equation. So then these are the x, y and z components of the v dot grad v. So if I see on the left hand side, these are the components of del v by del t. These are the components of f, and these are the components of v dot grad v. So v dot grad is a scalar quantity, so the direction comes from this. So it's this which will change from component to component. So in the x component, this will be Vx. So that is what you have over here. In the y component, this will be Vy. That is what you have here. And in the z component, this is what you'll have. So this equation can be written in compact form as So this looks like Newton's law, but the left-hand side seems a little more complicated. So this is the force per unit volume. This is the mass per unit volume. So this should be acceleration. But this, apart from the del V by del T, has a V dot grad V. So what is the physical significance of this V dot grad V? So that is what we'll come to in our discussion in the next class. So this is where we'll stop. Any questions?
Sir,